It's Theresa Windus, who comes to us from Iowa State University and Ames Laboratory. Theresa has a long history of leadership in the development of methods and algorithms for computational chemistry and then delivering them in games and NWChem. And she's going to tell us how her community is looking forward to the challenges of achieving Exascale in the next few years.
All right, well, thank you for coming to my talk this morning, and I appreciate the SC organizing committee for inviting me. And I also want to thank Paul for setting the stage for what I'm going to talk about today. So our application field is the chemistry field, and I'm going to talk mostly about two applications, NWChem X and games, which are both supported through the Exascale computing project, the ECP project that DOE funds. Okay, so one of the things I like to think about is sort of the big picture a little bit. And I liken what we're trying to do to making a manned mission to Mars. Okay, now I realize this is a stretch, okay, but that's the point. The point is that we're trying to do something that's really huge, really almost mind-blowing when you get down to looking at it, okay? Now, we've made a manned mission to the moon. How much harder is it to get to Mars? A lot harder, okay? I think of it as going from the petascale to the exascale. There's actually a quite large leap there that needs to be made. So it's something that can inspire this down-to-earth woman to think about something bigger than what I usually do. So, how big is Exascale? I can't even get my mind around it, to be honest. Okay, it's 10 to the 18th floating point operations if we're talking about flops. That's a quintillion flops per second, okay? All right, well, if there were 10 billion people on the Earth, which there are not quite that many yet, maybe in the next couple years, each of them would be doing 100 million calculations in 1 second. Well, not quite possible, because most of us can only do a computation in maybe 2 or 3 in a second if we're really good. It's on the order of the human brain processing power at the neural level. So you've all probably heard of the Human Brain Project. That's motivated by the exascale computing. I still don't have a good handle on it, though. So if I start thinking about sort of a everyday situation, if I take a football field and I include the end zones here, and I start piling up ping pong balls, okay, and if I just pile them up, it's 11 million kilometers, okay? That's a lot of ping pong balls. It's about 1/20th of the way to the Mars, and it's about 14 trips to the moon and back. That also gives you some idea of the difference between going to the moon and going to Mars, right? It's a big change. Another way of thinking about this is if I take one of my hairs, okay, and a hair width is about 10 to 100 microns. And if I start laying them width-wise, okay, so I lay them lengthwise against each other, and if I could stack them up, I would make about 220 trips to Mars and back, okay? Still, it's just a huge number, right? Can't get my mind around this. Earth to Mars. If I take an exa number of 200 nanometer particles, that will get me from the Earth to Mars, okay? Chemists like to think about this thing called a mole. That's 10 to the 23rd atoms or molecules, and that's getting close. It's not quite there, but it's getting close, right? 5 orders of magnitude off. That occupies about 6 gallons or 22 liters of space. And if we talk about actual nanoparticle, we're talking about, if we pack it together, it's a millimeter cubed, okay? So it's really hard for me to put my mind around all of this, but thinking about it, the nanometer scale, what this is kind of a fun and interesting exercise. So keeping with my my Mars mission theme, okay, we've got to have the scientific mission, the excellent people to do the work, technical requirements that we have to look at, and then we actually have to start thinking outside of our normal box. So these are the things that I'm going to talk about. So let's touch on that scientific mission first. So what is our scientific mission? It's to enable new frontiers of understanding, accuracy, and prediction in chemical properties. Well, okay, so we can already do some of that, but we do it at a very small scale. The chemistry industry is one of the largest in the world, and in the United States, it's about $800 billion worth of product that's being pushed out per year. Okay, it's a huge market. So if we can improve how chemical processes are made, we can actually make a great impact on a very important industry. So one of the important aspects of that is something that is catalysts. And catalysts help reactions to go faster. They lower the energy barrier, so maybe you don't have to have as high pressure, as high temperature when you're doing your reactions. And this is, of course, really important to the industry. So we have things like these heterogeneous catalysis mechanisms that is represented here. This is a mesoporous silicon nanoparticle, which is made at Ames Laboratory. This is work with the games folks, so run by Mark Gordon at Iowa State and Ames Lab. And the idea here is that we have these nanopores that hold a catalyst. We bring the reactions in, or the reactants in, sorry, and we then get the products out. Okay, so if we can design those catalysts to be very effective, lower the barriers, we're going to actually lower the cost of making the chemical. That's the idea. All right, so there's many different kinds of materials. So one is a zeolite. This is something we're focusing in on in the NWChem X project. One of the challenges is that we can do small amounts of this very accurately, but we can't do large amounts very accurately. And we have seen that there's cooperative effects that we must take into account that will give us the chemistry predictively. Another area that we're looking at in the NWChem X project is looking at creating better biomass. So for example, there's certain proteins that are important in looking at drought-resistant processes for growing biomass. So that's another example where we have to have the chemistry. We can't just look at the proteins themselves. We actually have to get into the chemistry of it. So that's a good part of our scientific mission. The other part that we have to look at is the machines that we're going to be targeting. Okay, so there's several good ones, and I've just mentioned a few that are in the DOE complex that we look at. So Cori at NERSC, Titan at the OLCF. You can see that they're by the same company, but they're quite different architectures. This makes it really challenging to have a platform for which we design and run our software, right? Every time there's something different, it means we have to optimize a little bit differently. Usually that's what it means. And Paul was very good at explaining what the next generation computers are. Of course, the ALCF was going to be one of our targets, but now their big machines shifted out to 2021. We still need to keep that in our thoughts, but we don't yet know what that machine's going to be, right? So how do we plan for that? That's a key part. So we're looking at the Summit machine at the OLCF as our first target since it's coming down in 2018. And so they currently have a machine called Titan, and they're switching over to this machine called Summit. And you can see that there's significant differences just between those two architectures. There's fewer nodes, they're fatter, they've got more memory, there's going to be higher bandwidth in the interconnects, and a much larger and faster file system. Okay, and if you look, they've gone from AMD Opterons to IBM Power 9s, okay, and from NVIDIA Keplers up to the NVIDIA Voltas. Okay, so the GPU part may not sound so tricky because you're staying with the same vendor, but any of you who've done any of that know that there's a huge difference between those two architectures. Okay, so even the early development machine that they have on the floor right now is Power 8 Plus, and it's the NVIDIA Pascals. So we're still not quite at the machine that we want, although it's moving maybe in that direction, right? And as we all know in this community, the target is constantly shifting, right? So we have to plan for that. Okay, I'm going to skip this slide. Okay, so another aspect of it is we need excellent teams, and Paul has already talked about this to some extent, but this is a really, really complicated process. Even if I just scope down to the chemistry part, it's already incredibly difficult to think about how I'm going to put this together and make it work on an exascale computer. Okay, so we have the NWChem and X and the games teams, and you notice I haven't put any names here, and part of that's because we have a very diverse team, and many different labs, many different people, and I am sure to miss someone. Okay, so the idea is I'm not going to miss anyone here, but know that I really acknowledge all the work that people are doing in here. Okay, and in those teams, we're currently being embedded inside of this ECP project, which has many, many other excellent teams that we want to take advantage of. So there's other application teams that are listed, and we also have to think about these software technology projects, right? What will we be able to use for the intranode parallelism and portability? What tools are going to be available there? Are we going to have to design them ourselves, or are we going to be able to take advantage of what's already being designed in the ECP project? Right? This adds to our risk inside of our project when we use someone else's software, but we can't design it ourselves. That's the whole point. We're at the scale where we just can't do it now. Okay? So we have to look at things like memory models, parallel models, code generation, data compression, et cetera. Okay? And what's really nice is the ECP project has all of these elements in it, and there's people we can go to and have conversations with. So it's really an excellent venue for us. Now, I don't want to neglect that there's other things going on, as we heard, in Europe or in other US entities, right? So the Air Force Office of Scientific Research has funded a co-design project that I was part of that really was looking at games and how to get that into a better parallel position, as well as looking at power pieces. Another one that I'm looking at and I'm involved in now is called the Molecular Science Software Institute. That's an NSF-funded project looking at software development practices. And I'll talk a little bit more about each of these in a minute, or a little bit. Okay, so you've got lots of really excellent teams and people. You have to bring them together, make it all work. So what are the technical requirements that I need to focus on to get myself to be launched up to Mars, right? How do I get there? Okay, so it's going to take me a lot of work to get there. And I'm just going to talk about a few of the things. So now I'm going to zoom in. I'm going to talk about NWChem in particular. NWChem has been around for a while. Since 1992, it was part of the construction project at the Environmental Molecular Sciences Laboratory at Pacific Northwest National Lab. And it was designed from scratch to work on parallel computers. Okay, realize back in that time frame, we weren't talking about petascale computers even at that time, right? NWChem has evolved a lot since then. It's an open source code. It's used by many users. We have a lot of downloads. We have a lot of people who are publishing results with this code. And we even have some pieces of our software architecture that are being used by other products or projects. Okay, so we have a very successful project already that we now want to take to the exascale. So we're calling that the NWChem X project. The main capabilities that are NWChem are legion. Okay, we've got lots of different capabilities, both in our software capability, in our methodology. So we have electronic structure, molecular dynamics, we have ab initio molecular dynamics, and each one of those has different hardware and software needs. Okay, so even within the electronic structure part, there's a lot of different hardware and software needs. Okay, so what are we going to do to be going up to the exascale? Well, we decided to make what I consider a fairly bold choice. We decided that our old architecture that was built on Fortran was not cutting it anymore. Okay, not that Fortran's necessarily bad, okay, but that we needed something new to be able to have the flexibility that we needed to accomplish the science that we were after. We currently have limitations in our architecture on scalability. Some of our algorithms that we need to move to, we just really can't fit very well into our current architecture. And we know that we're going to have more levels of parallelism than we've ever had before, and Paul touched on that before. So we're moving to a C++ code base. Okay, now part of the reason for the C++ is actually because of some of the projects that are going on in the ECP are really focused in on how do we get C++ to work better. And even if they've got a Fortran interface, it works better if you work in C++. Okay? The other things, everyone knows sort of some of the other advantages, the modularity, the programmability, et cetera. Now, some of the advances in Fortran give you pieces of that, but we didn't feel like it gave us enough. So we wanted to make this gigantic leap into the C++ world. So we're creating a whole new computational framework, which is exciting and scary all at the same time. Okay, this is the way it should be, actually, when you're launching it as something new. Okay, so we're developing some new technology, and I'll talk more about each one of pieces of this. But the idea is to get high productivity, high scalability, great performance, and hopefully get some portability out of all of this. Okay, so we're going to be initially looking at just a limited set of our electronic structure methods. Okay, just because we know we have to focus in to get that high accuracy that I talked about. Okay, and we're going to be implementing some basic things in our classical molecular dynamics and our ab initio molecular dynamics, because ultimately we need all of that capability to solve the scientific problem that we have. Okay, now it's not the focus of what we're doing, but we have to have some basic implementations so that we're thinking about it in our design process, right? So we're starting up from a full design and moving forward. Our technical goals, then, are to enable a broad range of new chemistry research, and the key here is with robust predictive capability. Okay, so we need to be able to control the errors, and that's something that currently, right now in our architecture, we have some limited capability of, but not enough. Okay, we also haven't looked at what we call sparse or low-rank technology enough, and that's going to require a very different architecture than we currently have now. The other thing I want to really emphasize is we need strong scaling. Okay, we can't just scale up the problem. We have to do that, but we also have to have strong scaling. We need the same size problem to run much, much faster. And the reason for that is because we need to do many, many points on our surfaces for doing molecular dynamics or Monte Carlo simulations. Okay, so what that means is we have to get down to minutes of getting energies and gradients, and maybe even seconds if we can push it that far, right, for very large systems. Okay, so we've got a lot of risks and challenges, as Paul mentioned, in our project, right? There's a lot of things that could stop us from going to the exascale, and I've just pointed out a few of them here. One is, are the performance of the parallel tools going to be there? We hope. You know, we don't know. And which one of those tools is going to be the one that's going to get us there, right? If we bet too early on the winner, we may pay for that in our architecture. So can we separate things to make sure that we're not just picking one software, that we're making our architecture flexible enough to pick many different parallel tools, whichever ones are going to work for whichever architectures? Unknown exascale architectures, you heard about that. And what if quantum computing actually becomes viable sometime in the near future, right? Our quantum chemistry applications are pretty ripe for that kind of an architecture. But we're not looking at that yet, okay? But it could come up. We have to have performance and scalability of our own algorithms. We have that within our current NWChem X project, at least to a certain point. Can we get there to the exascale, right? Okay, so that's just an idea of some of the kind of risks, and the mitigation here is to work with the vendors, the ECP projects, our collaborators, and to really just try to figure out, make sure we're communicating and getting as much information as we can, and trying to separate concerns. Okay, so let me talk about performance, portability, and productivity as just one example of an area we're worried about. The vehicle that we currently use for that is a symbolic algebra system that actually takes our symbolic representation of our equations down into something that looks a little bit more human readable. That's through the operator contraction engine, that OCE there. And then the tensor contraction engine takes those equations and puts them into code. Okay, we currently have that in NWChem. One of the challenges is it's not flexible enough to work on many different kinds of architectures. It doesn't separate those concerns that I was talking about before. Okay, right now it's working under the global arrays. We've had high success in using that kind of an architecture, but maybe that's not the best architecture for us moving forward. So the whole idea is to move forward with this code called TAMM, the Tensor Algebra Many Body Method. Okay, so it's going to be the TCE, the Tensor Contraction Engine replacement. And it's going to, hopefully, if we do everything right, allow us to very quickly develop software from our many different kinds of methods that we need to produce. Okay, so this is just a sample of the kind of methods we would like to be able to produce from our code. All right, so TAMM, okay, the new things with TAMM compared to the TCE is going to have to work on sparse matrices. It's going to have to be expanded to work with what we call various orbital spaces, so again, more flexibility. It's going to have the same kind of pieces of the domain-specific language that we want, and again, that's for productivity purposes. For portability, we're going to be separating out this concern of basically generating tasks and how they get scheduled. Okay, so we have to do more of that to be able to get performance on the exascale computers. And then we're also, of course, shifting into C++. So that means we have to think about how we're designing our classes and all of those sorts of things. The other piece is portability. If we do our job right and we allow for flexibility of all of these different ECP software projects that are out there, maybe we can build an API that will allow us to integrate multiple different things out there to have portability across the many different platforms. Okay. The other piece is we don't want to be doing a lot of hand generation of code. So this is an automatic code generation process, which is, it still needs some hand tuning, but the idea is to really, when we change architectures, hopefully work on the back end instead of working on the front end, where we're doing all of our mathematics in the science. Okay, so here's an example of TAMM's performance. We've already done some work. I'll say that you should focus on the graph on the left. Okay, our original code, you can see, gives the time to solution for an iteration for what we call a couple cluster or very accurate calculation. If we do some additional scheduling, we can actually get that time down. And if we actually include some operation minimizations, which is another ECP project, then we can even decrease our total time to solution more. So the idea is to have a lot of this automated inside of our software. Okay, inside of NWChem currently, we've been looking at how to do task management. And so one of the focuses of doing task management is really to eliminate synchronization points, be able to decompose our computations into finer grain parallelism, and you heard that that's going to be very important, right? Many levels of parallelism are needed. We need to be able to aggregate tasks, though, for higher locality, because the more communication you do across these machines, the less parallelism and scalability you're going to have, or less scalability you'll have, okay? And we want to decouple our data distributions from the load balancing and the scheduling, okay, and the algorithm itself, right? The algorithm should not care how that gets done on the machine. Okay, ultimately, that's really what it should come down to. So we want to separate those concerns as much as possible, and we want to overlap computation and communication so that way we get more scalability out of the whole process. So as part of that Kodash project I mentioned with the Air Force, we've been working with the PaRSEC team, who actually is also one of the ECP teams. And we've been taking our static representations of our code from the Tensor Contraction Engine and working it out to put in these task flow models. So what we do is we represent our code in terms of tasks and a network, okay, so graph formulation, if you will. And then we use PaRSEC to do all of the scheduling as a runtime scheduling thing, to be able to do the execution, decide the memory management, and looking at the heterogeneity of the machine as well, okay? And then it will do the mapping onto the computer for us. At least that's the overall goal, right? Okay, so I don't have a lot of time to explain this particular graph, but the black one is the NWChem original. The red bars that are sort of on the right side of the graph, those are NWChem using PaRSEC. And as we increase the number of cores per node, we see that the code is scaling much better, Okay? So the one on the left is using 64 nodes, the one on the right is using 128 nodes, and then we're just using more cores per node. Okay? And so we're getting about a 2 times effective speed up just by using these kind of methods. Okay? So really important to do this. Okay, if I'm going to Mars, I need to worry about power. Right? And I actually have to do the same thing if I'm worrying about running on an exascale computer. Now, personally, I don't have to worry about it. Someone else who's paying the bill has to worry about that maybe. But I want to be a good citizen, so we want to think about how we work with these resources that are using more effective use of power. Okay, so this graph was pulled from the Green 500 list, and you can see that the architectures over time are getting more and more efficient at using the power. But it's still a huge cost. Okay, so energy and cooling typically exceed hardware expenses by after about 3 or 4 years of being on the floor. Okay, that's huge. It's a huge expense. And if you look at what's predicted for the exascale, you're looking at maybe 20 to 30 megawatts of power, okay? And so you're looking at $20 to $30 million, okay, just to run that thing for 1 year. Okay, well, so let's do a quick comparison just to put this in context. If I was working on the brain simulation project, some of their predictions is they need the exascale computing to simulate the brain. It's going to take 4 petabytes of memory and about 20 to 30 megawatts of energy. Well, the human brain uses only about 20 watts, okay? So we're about 1 million times more performant, but of course, we don't do as many computations, right? So there's the trade-off. So there's lots of different things that we can do to improve that performance per watt. Some of that, of course, has to happen on the hardware. But what I want to focus in is that second point on energy adaptive algorithms. Are there things that we can do to help us? And I'm not going to claim I have any answers here. Okay, we've done a lot of work at trying to identify what parts of our algorithms are energy efficient, which ones are not. And we're in the process of looking at how can we adapt those to make them more energy efficient. Okay, so oftentimes you have this trade-off between your computational cost, so your time to solution, and the total energy that job took to run. Okay, so this is an example using games, okay, using a density functional calculation, and there's many more examples. I'm just pulling out one for you. Okay, where we looked at the normalized time, so that's just basically the time to solution per one of our variables, the basis set. And if you look at the Haswell outperforms ARM64 and ARM32. No real big surprises there, right, if you know those architectures. But if you look at the total energy used, well, ARM32 is the clear winner for the energy consumption, right? Question is, can you afford to wait that long for your calculation? Are you willing to do it? Okay, so there's these trade-offs between the time to solution and the total energy, oftentimes. But every now and then, you get a win-win. Okay, so this is work done in my group using NWChem. And we have this algorithm that's a disk-based algorithm. Okay, so maybe not the best algorithm for exascale, but as Paul said, we want to run on many different architectures, and there's a lot of systems out there that still have some good local disk or some good global file systems that we can use. So if I take this disk-based algorithm and I just run it on one node, okay, this is local disk now. What you're seeing on the graph is normalized time on the left and percent total energy used on the right. And the blue bar is if I run one process per core, okay, like we normally run. So just normal MPI processes, one process per core. The red one, the next one, is oversubscribing by 2. So in other words, if I had 6 cores now, I'm running 12 processes. Okay, so I'm double it, triple it, quadruple it. That's basically what I'm doing. So I'm oversubscribing the system with more MPI processes than the system has cores. And you can see by looking at the time to solution for this particular algorithm that if I oversubscribe by a factor of 2, going from the blue bar to the red bar, I get a huge savings in my time to solution. And even if I oversubscribe by 3, I don't get a huge improvement, but I do get an improvement. When I oversubscribe by 4, I start seeing that it goes back up. And what's happening? Well, probably a good number of you already figured it out. We're starting to overlap communication and disk I/O, or computation and disk I/O. Okay? With one process per core, there's not enough work. So when it starts to dump out data to disk or read it from disk, that core is basically sitting there doing nothing. Okay? And so when we oversubscribe, we can get swapping in and out of processes, and we're purely letting the operating system do this now. We're not doing anything fancy. We're just using more MPI processes. That's it. Okay? We can see that we get time to solution improvement, and we get energy improvement. Okay, so the total amount of energy we use goes down as well. Now, that's mostly because we have decreased the amount of time that we're using, right? There's probably no surprises there, but taking advantage of some of these simple things is actually quite a useful thing as well. Okay, one of the other pieces that we have to worry about is software engineering practices. NWChem, the current team, has a pretty good process in place already. But it's a little dated. Okay, so while we're in this whole redesign mode, can we introduce new software engineering practices that are also useful? So what we're looking at as we're doing this redesign is bringing in some more of those practices. Okay, so we've always had a repository, we've always done some code review, we've always thought about APIs, we've always thought about documentation. We're not always so good at documentation. Okay, so we've had some of these practices going, but we wanted to take it up to the next level. Because when you're talking about an exascale computer, you'd better make sure that your software is working well. And if you're building a huge consortium of packages that are putting together, you need to know where the failure is. I can't be chasing down a bug in a million lines of code, right? Especially when I'm running on an exascale computer. It's just not practical. So we have to do better software engineering, unit testing, better ways of incorporating our documentation in, better ways of doing correctness testing and performance testing. We need to do both. Our build system is dated. Let's just scrap it and start from new. We've got a whole new build system we're working on. Okay, so using some of these new, I would say newer processes that have been around a long time but haven't always made it into the high performance computing arena, that's what we're trying to do as we're redesigning NWChem. Okay, and one of the ECP projects called the Ideas Project is actually, that's what their focus is to bring good engineering processes into the ECP. Okay, and also, I'm going to talk now about this Molecular Science Software Institute, which that's its goal as well. So its overall goal is to serve and enhance the software development efforts of the broad field, now I'm talking very broad, of anything that's computational molecular science. So we would think of this as chemistry, materials, biophysics, et cetera. Okay, and the idea is to provide mechanisms and resources to improve codes and the workforce. Because I don't know how many of you out there are trying to employ people, but it's really hard to find really good people who have the experience you want with software development. We can find people who have, I should be careful here, we can oftentimes find people who have the math and the chemistry experience, but not so much have all of that software engineering practice behind it. Okay, in our community, that's a big problem. Okay, so interoperability is one aspect where MOISSI is important. And any of you who have followed the NASA missions, right, you've probably heard of the Mars Climate Orbiter. And it's the famous example of basic interoperability problems. Okay, so one team was working in expecting metric systems, units, and the other one was using English system, okay? And of course, what that meant was that as you fed information from one into the other, you were having problems. So the thrust and the navigation were thrown off, and the Mars orbiter actually ended up going into the Mars atmosphere and was lost. Okay, a big project that was lost over what seems like a really small thing. Right, but we have to worry about that because if we're going to be relying on other people's software, we better know what they're giving us, and they better know what we expect. Okay, so we need to worry about our abstract programming interfaces, what are the units coming across, all of that information. So interoperability is a big piece that plays a huge role for us. Okay, so what MOISSI is providing is expertise. We've got software scientists on staff who are working with the research community in the molecular sciences to develop and test and deploy and maintain code infrastructures. Okay, and we're also doing a lot of educational and outreach and training activities. So we do summer schools, we're doing a lot of online training, taking advantage of lots of online training that many of you have probably already put in place. The idea is to use all of that into our community for chemistry. Okay, and then what we're trying to do is to get this community of people who don't always like to work together to come together and to develop some standards, or if not standards, at least think about how do we take one set of data and transform it into another set of data, and do that in an effectively consistent manner so we can trust it. Okay, so best practices and curation tools, et cetera. And I'm going to make a pitch. Okay, so we need software scientists. We need people who in different areas, okay? We need people who are molecular scientists. We need people who are computer scientists. We need people who are software engineers, okay? And we also need applied mathematicians, because all of these people together is what it takes to build these big ecosystems. So if you know of someone who's looking for a job, or an upcoming student or postdoc who's looking for a job, please have them come talk to me or go to the website. All right, off my pitch. All right. So, thinking outside the box. I mean this literally, okay? We got to think outside of the exascale box. We have a problem. Exascale computers, with as big as they are, that I can't even imagine really the number of flops, okay, are really only going to give us about a 50 to 100 increase in the computing capability that we currently have. Okay, I mentioned the molecular systems that we're looking at that are really important for industry here. And we can't get to the size of system that we need just by exascale computers alone. Okay, so for very high accuracy, we need probably about 1,000 atoms. Currently, we can do maybe about 100 atoms at this really high accuracy method. Okay, because these high accuracy methods scale as the number of atoms to the 5th or the 8th, for example. Okay, so really high scaling. To get to even bigger systems, we're going to take that accurate method and we're going to embed it in a lower accuracy method, which is usually, well, some people would say end of the 2nd. I'll say formally end of the 3rd to the 4th. Okay, currently we can do maybe 1,000, 10,000 atoms. We actually need to get that higher, up to about 100,000 atoms. A factor of 50 is not going to do it. Actually, with the kind of scaling we're looking at, we're only going to get about 1.3 to 2 times the number of atoms as we had at the petascale. Really disappointing, right? I mean, in some ways it's heartbreaking. But this is where really clever people come into play, okay? And I'm not going to claim to be one of those. We've got really great people on our team who are looking at these reduced scaling algorithms. So in other words, how can we take something that goes from end of the 5th down to, say, maybe end of the 3rd, okay? And so there's a bunch of methods listed here. I'm not going to go through all of them. I'm just going to point out 2 of them. One is the fragment method, and then one that's the Cholesky decomposition type approach. So in the fragment molecular orbital model, basically what you do is you take the big system and you just chunk it up into little fragments. Okay, now I say just, but there's a lot of science that goes in figuring out how you do the chunking and how the chemistry works between the chunks. Okay, so once you've got those chunks, we call each one of those chunks a monomer. You can use something called a many-body expansion to take those monomers, and you can calculate the monomer, you can calculate the dimer, subtract out the monomer interactions to get the dimer interactions. You can do trimers, and the idea is that as you continue expanding out this expansion, you get more and more accurate results. Okay, now if you did all the monomers together, you'd be right back to the same result you were at the beginning. Okay, but the idea is to break up the system into small enough pieces that we can then distribute those across a big computer, right? Because they're all independent in some sense. Gives us another level of parallelism that helps us to get scalability. Okay, so real quick because my countdown's going down. The key here is that if you use these kind of methods, you can get very large systems down to a small amount of time in computation. So you'll see that as these graphs keep going down, they're going down into minutes regime here. So now we can start really thinking about doing those molecular dynamics and Monte Carlo simulations that I mentioned that are necessary for the science we want to do. Okay, another way of doing this is if we take a look at, say, our integral tensor, and just think of it as a matrix, for example. Okay, the one on the left is the form that we normally get out of our computations. But if we do some rearrangement, basically looking at mapping on the large integral pieces, we can get that into more of a block diagonal form. And the beauty of that is it decreases the amount of communication you need to do across the calculation, and it localizes the data, and it localizes the computation. Okay, so you get a big increase in just the localization, which gives you more scalability. Okay, so that's all I have time for on that one. Okay, so last thing is we need to take off, and we're at time to take off. So we are getting ready to, hopefully launch this project with some real code. We're working on that code and hope to have something available within the next 6 to 8 months that people can start playing with. Because we've been in a design phase for quite a while, and if you've ever done this, you got to design well. Right? You got to think about it really carefully. All right, so again, I'd just like to acknowledge the different teams, the different funding sponsors, and all of the fabulous people who I wasn't able to name by name. Just thank you so much for your contributions, and thank you all for your attention.
We have a few minutes if there are any questions for Theresa. Anyone? Oh, Frederica? Oh, there. Oh,
hi.
Oh, we have one. We have one back. Actually.
Oh, there we go.
Can you go back?
So can you hear me?
Yeah. Oh yeah. Why don't you start?
So I'm Cuthill-McKee with NIST, and I wanted to ask you, to what extent do you think about security of the system that you develop, or the
security of the software?
Software, as well as the networking or access to the people, everything. Overall security of the system in terms of technical requirements for your system.
So we've been fairly open. We've tried to be fairly open, mostly because we know that there's a lot of really smart people out there, and they might have some solutions we haven't thought of. So we currently have a private repository. That's about the closest we come to thinking about security in some sense. The reason why we're doing that is just because we're still in prototyping phase. There's a lot of changes happening, and we don't really want the whole world to see that before we're ready to at least show you what we think the basic architecture is going to be and how it's going to move forward.
See, okay, so we have a question from Frederica. In the back, can you enable Paul Messina's microphone? The other speaker's mic? And Frederica?
Yeah. I'm Federica Derima from IFOSR.
Sorry, I can't hear you.
I said, maybe I should speak to you closer. I'm Federica Derima from IFOSR, and I appreciate the support we give you and the work you do for us. So you talked about, this is use. You talked also of thinking out of the box. And of course, as you know, in our case, not only we want to understand the combustion, but eventually control it, all right? So how do you see the advances in femtosecond, attosecond laser that allows you to also observe the chemistry, would allow us eventually to do these things in real time also and control it?
Okay, so
your thoughts on that?
Yeah, if I understand the question right, so you correct me if I'm getting this wrong. So if you're looking at combustion processes, for example, where you've got very quick processes, how do we see the, I've already lost it. Oh, can we do like, Right, so real-time examination of the system using things like femtosecond laser spectroscopy and things like that. So that, some of the methods that I sort of glossed over are for excited states, and there is some work in the team to do some real-time calculations. That's part of a SIDAC project, actually. And so while we're not focusing in on that to begin with, certainly we hope to bring all of that capability and functionality into the end result, maybe 10 years out. But we currently have that functionality in NWChem X, and it's being built up, in NWChem, and it's being built up now. Yeah.
Let's thank Theresa one more time.